So technically, we've only supposedly talked about U substitution in the context of the power rule or e to the something or natural log of something. Sorry, 1 over something. But really, I feel like we've kind of discussed U substitution quite a bit. Like, we know that you can kind of do a U sub for any sort of function where the insides are more complicated. For example, we could certainly, and we're not going to do all these integrals, but I'll point out, like, if someone asked you for the integral of, say, cosine of x cubed times x squared dx, we would certainly make the choice of letting u equal x cubed. D would be something like x squared, and eventually this integral would look, I'm not going to write it exactly, I think it'd be good for you to do this is going to become something similar to, which is often what I use that symbol for, the integral of cosine of u du. I'm gonna be off by a 1/3 somewhere. Come on in, but that's the idea. Or if someone asked us to find, like, say, the integral of, sure, that's terrible there. I need to clean that. X cubed times e to the x to the 4th plus 1, we would make the choice of letting u equal x to the 4th plus 1. And we get the same sort of thing. This would eventually become something akin to the integral of e to the u. Yeah, there's still a constant multiple that I haven't adjusted for yet, but I know you know how to do that at that point. One more kind of generalization here. We could do something like the integral of, I like that, yeah. X squared plus, I have to be careful here. Let's be extra careful. 3x squared plus cosine of x over x cubed plus sine of x. And here we could make the choice of letting u equal the denominator. And I will write it here. The du is exactly 3x squared plus cosine of x times dx. So here we could exactly rewrite this as the integral of du over u, which would be the natural log of the absolute value of u, which would then become the natural log of the absolute value of x cubed plus sine of x. So the point I'm trying to make here is that at this point, we have seen enough examples of U substitution that we kind of have a good idea of what's going on. You're typically trying to make a choice for u so that two things happen. One, you're picking a u that's stuck. The x cubed is stuck inside the cosine. This x to the 4th plus 1 is stuck inside the exponent. This x cubed plus sine of x is stuck inside the denominator. And more importantly, you want your choice for u to be such that the derivative of u is also somewhere in your integral. So here the derivative of u is 3x squared, and we certainly have an x squared times dx, and we can adjust for the 3. Here, your derivative of u would be 4x cubed, and then we multiply by dx. And oh yeah, we've definitely got an x cubed times dx. So we've got everything we want here. But then sometimes there are other u sub problems where you don't get all the things you hope to have. Like this problem. So this is kind of u sub with less goodness. So for example, the integral of x squared times the square root of x plus 9 dx. In this problem, I would still make the choice of u being x plus 9, because the x plus 9 is stuck inside the square root. And then I'm going to go about my usual way. I'm going to find my du. And here things actually do kind of work out okay in that the derivative is just 1. So my du is 1 times dx. The problem with this particular example is there are leftover x's after I deal with my du dx and my thing with u. So we start rewriting this. This is going to equal the integral of, I don't know what to do with that x squared, so I'm just going to leave it for there for a second. And then the dx becomes du, and then the square root of x plus 9 is the square root of u. But I can't have an integral that has x's and u's in it. So I do something like this where I have leftover x's. I then have to go back to my u choice and solve for x. So subtracting 9 from both sides, u minus 9 is equal to x. And then I can replace that x squared, I can replace the x there with u minus 9. So I can rewrite this as u minus 9 quantity squared times the square root of u du. And now the only choice we have is to multiply the whole thing out. So we're going to rewrite this as, well, just u minus 9 squared is u squared minus 18u plus 81. All of that multiplied by, instead of the square root of u, we're going to write u to the 1/2. And then we're going to distribute the u to the 1/2 to each term, meaning we're going to add powers. So we're going to get u squared times u to the 1/2, which is going to be u to the 5/2. 18u times u to the 1/2 is going to give us 18 times u to the 3/2. And 81 times u to the 1/2 is just 81 times u to the 1/2. And now we're finally in a place where we can find the antiderivative. So antidifferentiating each term, we're just going to add 1 to the power. So we're going to get u to the 5/2 plus 1, which is u to the 5/2 plus 2/2, which is u to the 7/2. I don't want to write divided by 7/2. I want to write multiplied by 2/7. Same deal here. We're going to get minus 18 times u to the, notice I'm leaving space here, u to the 5/2 times 2/5 plus 81 times u to the 3/2 times 2/3 plus c. I would do some minimal simplifying here. I wouldn't actually, if I didn't have to plug back in that u was equal to x plus 9, I'd probably just leave it as is. I wouldn't simplify those coefficients really. But since I'm going to go ahead and write another step where I plug in x plus 9 for every u, I'm going to do a little bit of simplifying as well. I'm going to get 2/7 times x plus 9 to the 7/2. 18 times 2/5 is 36/5 times x plus 9 to the 5/2. And then finally, 81 times 2/3. 81 divided by 3 is 27. 27 times 2 is 54. So 54 times x plus 9 to the 3/2 plus c. This is an example of what's called a back substitution, where you do a u sub, and then you've got some leftover x's, and you have to back sub into, I feel like that word is not the best word, but it's what it's called. We have to solve for x and then substitute back in for the remaining x's that are left over. Questions about this before we do another example? Okay, let's look at another example. Let's see. Yeah, seems like all right. Yeah, that's fine, I guess. So let's look at the integral of e to the 2x over e to the x plus 1. And so we're about to, after we do a few of these examples, we're about to learn kind of a new method, which is going to be iteration by parts. And then we'll kind of see that we have choices. But for now, still, if you see an integral and you kind of don't see directly how to do it, then you start throwing things at it. And the only tool we really have to throw at integrals right now is u substitution. So what's kind of the only plausible choice for you here? Or what do I think it is anyway? I think it's the denominator, e to the x plus 1. And the reason why is because that thing in the denominator is stuck there. I really emphasize the stuckness of things, right? If something is stuck in a place where you can't manipulate it really, then that's a good candidate for you. It might not be the right choice. Maybe this is the wrong choice, but it's a good starting place. So then we're going to find our du. Our du is the derivative of e to the x times dx, which is e to the x dx. The derivative of 1 is 0. And then I'm going to notice that I do actually have that. If I am careful here, I can rewrite the top as e to the x times e to the x over e to the x plus 1 dx. And then one of those e to the x's I can group with my dx and say, oh, great. There's e to the x times dx, and that's equal to du. Oh, interesting. I never would have thought about it that way. Sorry, I just was realizing you could totally do this another way, which is kind of cool, but I wouldn't. Yeah, I wouldn't. So then we can rewrite this as the integral of, well, I like to deal with the du part first. So du at the end. The denominator is just our u. And the numerator, I'm going to briefly write as e to the x. But then I'm going to say, oh, well, I have leftover x's. I need to solve for them. Now, here's the nice thing. This is why I actually want to write it like this before I do the other thing. I don't actually need to go all the way down to solving for x here. If I take my u equal to e to the x plus 1 and start trying to isolate x, if I subtract 1 from both sides, I get u minus 1 equal to e to the x. And since I have an e to the x, I can stop there and just say, oh, e to the x equals u minus 1. I don't have to say that x is equal to the natural log of u minus 1. Only go as far as you need to until you see the thing that you're trying to replace. So this is going to replace our e to the x. And we're going to get, now this integral is equal to u minus 1 divided by u du. And now we've got a rational looking thing with a single denominator. We divide each numerator term by the denominator. So you get the integral of u over u minus 1 over u du, which is really the integral of 1 minus 1 over u du. And now we're finally at a place where we can find the antiderivative. That's going to equal the antiderivative of 1, which is not x, it's u in this case, because it's with respect to u, minus the integral of 1 over u, which is the natural log of the absolute value of u. Let's see. We plug back in what u is equal to, which is e to the x plus 1, and we get e to the x plus 1 minus the natural log of the absolute value of e to the x plus 1. Let's see. Interesting. Yeah, that worked too. Okay. Sorry, I'm just thinking about something. Okay. Sure, we'll do 2 more. So these are examples of what are called back substitutions. Again, where you have leftover x's after you do your u sub, and you have to fill them back in with whatever x is equal to in terms of u. Sometimes we have other things that are kind of weird as well. And this is just kind of to finish talking about the things that can happen with the u sub. Most of the time, the nice thing happens where you pick u and the derivative is already there. These are examples where you pick u and the derivative is there, but then you've got some extra stuff left over. Or sometimes, and I feel like this is kind of the worst time, you do an integral like 1 over 1 plus the square root of x. And there's really only one plausible choice for u here as well. U equal to 1 plus root x. But the problem with that choice, or the kind of disappointing thing with that choice, is that if you try and find du, it's not going to be super helpful. If I take the derivative, if I rewrite this as u equal to 1 plus x to the 1/2, just to make it easier to differentiate, my du is going to be 1/2 x to the negative 1/2 times dx. Or if you prefer, 1 over 2 root x dx. And I really don't have a 1 over root x times dx. We can't separate the 1 plus root x there. This is really a 1 over 1 plus root x times dx, which is very different than that, unfortunately. This doesn't really help us. This is not helpful. So if this is the situation where you've chosen u and there aren't really any other candidates for u, and your du looks kind of terrible, we do this. Yeah. Save myself there. We solve for x. So I'm going to square both sides here. So u, not first. Whoa, before I square both sides, what am I going to do first? Thank you. Yes. Subtract 1 first. Not that you couldn't square both sides before that, but it wouldn't be nice. And now we're going to square both sides. And we're going to say that u minus 1 squared is equal to x. And then we're going to differentiate both sides kind of the other way, meaning instead of finding du dx, we're going to find dx du. So we're going to say that dx du is equal to the derivative of u minus 1 squared, which is 2 times u minus 1 to the first. Or dx is equal to 2 times u minus 1 du. And look, now we have the things we need. We know what dx is equal to. And we know that the denominator, 1 plus root x, is equal to u. So we can totally rewrite this integral in terms of the letter u instead of the letter x. So we're going to write this as the integral of 1 over u times 2 times u minus 1 times du. And now we're in a very similar situation to the last problem, right? In the last problem, we were integrating u minus 1 over u. It's essentially what we're integrating here. I'm going to pull that 2 out in front to have the integral of u minus 1 over u, which is really just 2 times the integral of 1 minus 1 over u, which is going to be 2 times u minus the natural log of the absolute value of u plus c, which will then be 2 times u minus 2 times the natural log of the absolute value of u. And some people call this a power substitution because you're kind of finding x often as a power of u and then differentiating it that way. But the real key here is that if you notice that du doesn't look like it's helpful, go back to your choice for u, solve for x, and then take the derivative of both sides and get dx equal to whatever it's equal to. Some people skip this, some people cover it, so I feel like we should let's do one more example, and then we'll move on to some integration by parts. Yeah. One more example. I could number these. I meant to number these. Sure. Yeah, I can throw some numbers on this real quick. 1, 2, 3. Cool. Numbers. All right. So look at number 4. Something else that looks kind of awful. The integral of the square root of 1 minus the square root of x. To me, you could maybe make the argument that there's 2 plausible choices for u here. You could either pick u equal to root x or 1 minus root x. I would tend to always pick the thing that had the constant as well, because adding a 1 to your thing doesn't really change your derivative at all. Yeah, we're changing the sign, but okay, that's not that big a deal. So I would not choose u equal to root x. I would choose u equal to 1 minus root x. So then, looking here, your du is going to be similar to last time, right? The derivative of the square root of x was 1/2 x to the negative 1/2. The derivative of negative square root of x is going to be negative 1/2 x to the negative 1/2, or if you prefer, negative 1 over 2 root x dx. And again, we can see that that's not super helpful. I don't have a 1 over 2 root x, and I don't really want to do anything algebraically crazy to make it so I have a 1 over root x. That's usually not going to be helpful. So instead, we do the other thing. In fact, I want you all to do the other thing. So I want you all to take this equation, u equal to 1 minus root x, and solve for x. I would recommend bringing the root x to the left and the u to the right, and then squaring both sides. Done that, then you can find dx. But yeah, teaching here on Mondays and Wednesdays after lunch, like from 1 to 2. So I was just like, oh, I feel like it's like, I thought it was after lunch, and I was like, where am I going after this? Oh yeah, no, back to my office after this. Okay. Anyway, solving for x here, I would rewrite this as the square root of x on the left equals 1 minus u on the right, and then square both sides. X equals 1 minus u quantity squared. And then to find dx, The derivative of the left side is 1 times dx. The derivative of the right side is 2 times 1 minus u to the first times -1 because of the chain rule du. Now I have all the pieces I need to rewrite that integral that was in terms of x in terms of u. So we're going to rewrite this as the integral of the square root of u times 2 times 1 minus u times -1 du. Something you might see people do often is if you have two things subtracted oh my God, if you have two things subtracted multiplied by -1, sometimes people will quickly just rewrite that as the opposite order subtraction. 1 minus u times -1 is -1 plus u, which is u minus 1. It's a pretty standard, I don't even want to say it's a trick, pretty standard technique. People just do that all the time. So I'm going to rewrite this integral as 2 out front, square root of u, I'm going to rewrite as u to the 1/2 times this thing here, which is u minus 1. Again, the 1 minus u times -1, I'm just distributing there and saying I'm getting -1 plus u, which is the same as u minus 1. That's happening there. And people will often just be like, boom, boom, skip there and not show any steps there because it feels obvious to them. And then distribute the u to the 1/2. U to the 1/2 times u to the 1 is u to the 3/2. U to the 1/2 times 1 is u to the 1/2. And now we're in a place where we have powers of u, so we can anti-differentiate. We get 2 times u to the 5/2 times 2/5 minus u to the 3/2 times 2/3 plus c. And finally, subbing back in what u is equal to, we're going to get, and let's distribute the 2 as well. So I'm going to get 2 times 2/5 is 4/5. And it's going to be 1 minus root x, the 5/2. And then 2 times -2/3 is minus 4/3 times, again, u, which is 1 minus root x to the positive 3/2 plus c. Another example of what we typically call a power substitution, where you make a u substitution, but then you can't solve, then your du isn't helpful, so you solve for x and then differentiate and plug in whatever dx happens to be equal to. All right. Before we move on to start talking about integration by parts, not that we'll never talk about u sub again, because u sub is kind of always on the table, right? Just like with integration, just because you learn new differentiation differentiation, just because you learn new differentiation rules doesn't mean you never use the older ones again. Same deal here. U sub is gonna, I think of it as like, it's your go-to method. If you don't know what to do for an integral, it's not obviously a power or something else or some sort of trig thing you would just know. The first thing you typically want to try is a u substitution. And sometimes it'll work. A lot of the times it'll work. Sometimes it won't. For example, the integral of, let's do, I don't know that one. Let's do this one first. X times cosine of x. There is not a good u substitution here. If you let u equal x, your du is, in fact, I will point out, I shouldn't even say that, because u equals x is never the right choice for a u sub. Because if you let u equal x, then you're just changing the letters from x's to u, but it's still the same integral. And letting u equal cosine is not going to work out for me because my derivative would be negative sine. I definitely don't have a negative sine of x dx. So we need a new method. And it's actually kind of interesting, I think. U substitution kind of comes from undoing the chain rule. You're trying to find the inside derivative thing, or the thing that whose derivative is the inside thing whose derivative is also there. So U sub is a lot like undoing the chain rule, and actually integration by parts is kind of like undoing the product rule. here's how it works. So this comes from the product rule. I'm going to really want to emphasize here that when you do integration by parts, what you're actually doing is you're rewriting the integral so that you have some new piece minus a simpler integral. So when you do integration by parts, the first step is to rewrite it in some new way, and then you still have to do the integral of something that's hopefully easier. Let me show you what I mean. So very generally, here's the product rule. F times G, the derivative of F times G, if you remember, is F prime times G plus F times G prime. Usual thing. Okay, for some reason, someone decided once upon a time that we don't want to use those nice, different looking letters, and we'd rather make it more confusing and use letters that, if you're not careful, look too similar to each other. For some reason, we're going to use U and V instead of F and G. I literally could not tell you why, except that it's always written using U and V. Those are just the normal letter choices, so we should fall in line and do it like everybody else, because otherwise it'll be like, what are they doing over there? So then I'm going to write this slightly differently. Instead of writing U prime, I'm going to write du for the derivative of U. V is still V. U is still U. And then instead of writing G prime, I'm going to write dV. And now we're going to integrate both sides. So the integral of the derivative of U times V is equal to the integral of du times V plus the integral of U times dV. Okay, important question. Important question that I think you all know the answer to. What's the integral of the derivative of a function? Just the function. Maybe with a plus c, but we're not really worried about it. Right, the derivative and the integral undo each other. So if you do the derivative and then do the integral of that, you get back to where you started. So this left-hand side is just U times V. And then rewrite this just slightly. Instead of writing du times V, I'm going to write this in a way that looks more like how you actually write an integral, which is the integral of V times du plus the integral of U times dV. And then finally, we isolate the U times dV and we rewrite this as uv minus the integral of V du equal to the integral of U times dV. Or actually, because I've written it kind of backwards, I suppose. Typically, we think of integration by parts as the integral of U times dV equal to U times V minus the integral of V du. And the idea here is that this is going to be the integral that you start with. And we're going to make choices so that when we rewrite it, this new integral here is easier to handle, easier to integrate. That's the whole idea, is we're going to take our, in fact, let's just do a problem instead of me saying more words. I'm still going to say words, but like, I'm going to say words in context. So for this example here, the integral of x times cosine of x, we are going to make choices. We're going to say, okay, U is this piece and dV is this piece. And then when we rewrite it this way, the integral part should be easier. So the question then becomes, how do you decide what to pick for U and what to pick for dV? Very broadly, you want to pick the thing for U so that when you take its derivative, it gets simpler in some sense. So sine and cosine, not usually a great choice for U because their derivatives are sine and cosine. They don't really get simpler, although they also don't get more complicated. On the other hand, letting U equal like x or x squared or x cubed generally is considered to be a good choice because the derivative of a power of x is a one less power, which is quote unquote simpler. Again, the definition of simpler here is very kind of vague. So here, we're going to let U equal x. I want to remind you, everybody, I said earlier today, just a little while ago, for a U sub, you never let U equal x. Because all you're doing is wasting your time rewriting the problem with U's instead of x's. In integration by parts, it is totally valid and often the right choice to let u equal x. So just be aware. The nice thing about once you choose your u is after you've chosen what u is, dv has to be literally everything else in the integral, except for the integral symbol. So dv here is going to be cosine of x times dx. And yes, you should have the dx there. If you have a d on one side, you should have a d on the other side. And then we're going to find du. So taking the derivative, du is equal to, well, the derivative of x is 1 times dx. And then to find v, we take the antiderivative of cosine. The antiderivative of cosine of x is sine of x. One other kind of nice thing to know is that we want to pick u so that the derivative of u is simpler. We want to pick dv really so that the antiderivative is doable, and ideally so that it doesn't get more complicated when you anti-differentiate it. It doesn't have to get simpler, but we'd like an equal level of complication, if that makes sense. And we would consider sine and cosine to be equally complicated, right? They're pretty much the same function, really. Like they both have this shape, this sinusoidal shape. So let's rewrite this. We're going to rewrite the integral of x times cosine of x dx, which again is the integral of u times dv, equal to, I'm not going to write u times v here. I'm actually going to plug in what u is and plug in what v is. So I'm going to write x times sine of x. And then sure, if you want, we can think of that. Oh yeah, that's my u, my v, minus the integral of v times du, which is just dx. And again, I want you to observe here that, oh yeah, this new integral here in my total rewriting of the integral of x times cosine x, the integral of sine of x is much easier to deal with. It's actually something we know compared to the integral of x times cosine of x. So now we finish it off by evaluating it. We get x times sine of x minus the antiderivative of sine is cosine or negative cosine? Thank you, negative cosine of x. Plus c, and then I would take the one moment to rewrite this as x times sine of x plus cosine of x plus c. And that is the antiderivative of x times cosine of x. So typically when you're using integration by parts, you're going to pick u to be a thing whose derivative gets simpler. Now, more broadly, how do we know when to do what? Well, let me say a few words here. So when do we use integration by parts? So I would say the first thing we're going to look for is you need to have a mixture of functions. So one, when we have a quote unquote mixture of functions, meaning two or more different types of functions, two or more, really it's usually exactly two. Like you don't usually have a mixture of three types. And what do I mean when I say types? Well, the types that we often run into are something like, for example, the integral of x times e to the x. You have, or even x squared times e to the x, right? You have x to a power and you have an exponential function. Or you might have x to a power times a trig function. Or you might have an e to the x times a trig function. Or you might have an x to a power times a logarithmic function. All these are representative of having a mixture of two different types of functions. And the four types that we typically see in this class are logarithmic functions, algebraic functions, which is not my favorite way of referring to it, but basically when we say algebraic, we mean like a power of x, x squared, x cubed, square root of x, x to the negative fifth. All those are algebraic, or as I like to say, any power. And then we have trig functions, and then we have exponential functions, meaning e to the x. And this is the order that we usually try. It almost always works. Occasionally there are weird ones where it doesn't. This is usually the order that you try picking u in. So if you see something that's a mixture and you think you need to use integration by parts, you're first going to try letting u equal to a logarithmic thing if you have a logarithm. If you don't, then you're going to try letting u equal a power of x, like x squared, or x to the first, or x cubed, or x to the 1/2. If you don't have either of those things, you're going to let u equal a trig thing, like sine, or cosine, or tangent, or secant, or whatever. And finally, if you've gotten to the last thing on the list, it means you probably don't have a mixture, but you almost never let u equal to e to the x, although you certainly could try. The second condition or requirement that we usually have is, first you should have tried u sub. So when do we use integration by parts? When we have a mixture and we've already tried u substitution and it didn't pan out. Typically, an integral won't be doable either way. Meaning, if you have some integral, either u sub will work or integration by parts will work, but not both. Let's look at some examples. So for example, the integral of x times e to the x squared. Okay, it's definitely a mixture. I have an exponential thing, e to the something, and I have any power of x. I have an x to the first multiplied by it. So there's my any power, and there's my exponential. But before I go and start trying to use integration by parts, I should first look to see maybe there's a u sub that's going to work out here. So before I do anything else, I'm going to say, well, I think I might try letting u equal the thing that's stuck inside the exponent. But let u equal x squared. Is my du helpful? What's my derivative of x squared? Right. So my du is 2x dx. Is that going to work out in my favor? I think so. I have an x times the dx. So I should rewrite this as 1/2 du equal to x times dx, and then rewrite my integral in terms of u. My e to the x squared times x times dx is going to be, well, x times dx is my 1/2 du, and my e to the x squared is my e to the u. So this one was a u sub, even though it was a mixture. Many mixtures end up being u sub type problems. Many of them don't. Finishing this off, we get 1/2 integral of e to the u, which is just 1/2 e to the u plus c. And then we plug back in what u was equal to, which is x squared. So our answer here, the antiderivative of x times e to the x squared is 1/2 times e to the x squared plus c. No integration by parts necessary. The intuition here kind of starts to become that u substitution is useful when like the inside of a function looks like the derivative that looks like some other piece, right? It looks like you've done a composition of functions here. You have an f prime of g times a g prime. Whereas integration by parts, you're going to use if it looks like more like things are products. You have one function times another function. I know, yes, we have a product here as well, but that's your kind of job over the rest of these order is to kind of help figure out when you see one thing versus the other thing. So let's look at another example that's going to look kind of similar, but it's going to be very different. Yeah. Let's say we have, sure. Sorry, did you want to see anything here? So, yeah, sorry, no, you're good.
Oh, no, all right.
So you certainly could say 1/2 times c, but then 1/2 times c is still a constant, so we don't typically say that. I will point out that idea right there that we're talking about, like does that constant multiply the other constant? that does come back as mildly important when you start when 16C, when you're doing differential equations and you're solving for the particular solution. So sometimes you have to be a little bit careful about, does the thing out here multiply the constant over there? And sometimes it does, but we'll talk about that next quarter if you're taking 16C. By the way, there's a co-class for 16C. I made a Canvas announcement a while ago about it. I don't remember what time the class is. I think it's Monday, Wednesday, Friday, 1. So if you can't sign up for it because it's conflict, don't worry about it. You still can come whenever you can come and get added to the Canvas and all that jazz. So you don't have to register for it, but if you want to register for it, you're certainly more than welcome to. Let's look at this next one, which looks almost the same, but not really. The integral of x times e to the 2x dx. And here, a u sub is not going to be the way to go. If I try to u sub, which again, you should always think about first. You can think about it and discount it right away, but you should at least go through the mental gymnastics like, oh, could I do a u sub here? Well, let me see. I would, if I was going to do a u sub, I would let u equal 2x. And then my du would be 1/2, sorry, not 1/2, would be 2 times dx, and then 1/2 times du would equal dx. But then if I start replacing things, it's not really going to help me out because I'm going to have my dx being 1/2 du. My e to the 2x is going to be e to the u. And my leftover x here, if I solve for x, my leftover x is equal to u divided by 2. And so really, I mean, yeah, it's different a little bit. It's off by a constant. It's equal to 1/4 integral of u e to the u. But that's still essentially the same integral I had before. The integral of x e to the 2x is pretty much the same as the integral of u e to the u, just by a different constant. So this is not the way to go. No, does not work out so great. So we saw a mixture, we tried to use sub, it didn't work. So then we move on to integration by parts. So, okay, integration by parts. Using the LATE acronym, which is what people usually call that, the LATE, do I have a logarithm in my integral? Definitely not. So I move on. Do I have a power of x? Yes, I do. I have x to the first. So we're going to let u equal x. And as soon as you have chosen u, you should immediately write down what dv is equal to. I want all of you to write down what dv is equal to. We have no choice once I've picked u equal to x, or once you've picked u equal to x, or whatever u happens to be. All right, there's no mystery here. dv is everything else. It's e to the 2x times dx. And then we rewrite the other things. Our du, not rewrite, we find. We're not rewriting, we're finding the other things. The derivative of x is 1 times dx. And then the antiderivative of e to the 2x, by the way, here's one of the reasons we spent some time way back when doing those mini u substitutions. I don't want you to have to spend time doing a u sub to find the integral of e to the 2x. We know that the integral of e to the 2x is e to the 2x divided by 2. Because the derivative of e to the 2x would be e to the 2x times 2. And the 1/2 of the 2 would multiply out to 1. And now we can rewrite, and I am going to write this as the formula for a second here just to tell you something that I think is fun to say. The integral of u dv is equal to, here's an acronym? No, that's not the word. What's the word I'm looking for? And a mnemonic device that I have never been able to forget. Your integral of u dv is equal to the ultraviolet super voodoo. UV, ultraviolet, right? UV rays, super voodoo. Ultraviolet super voodoo. Can't forget it. So then, actually writing out what we have, the integral of x e to the 2x dx is equal to u times v. So x times 1/2 e to the 2x minus the integral of v du. 1/2 e to the 2x dx. Normally, not normally. A lot of the times I would bring this 1/2 out in front, but it's not super important here because we can kind of just imagine it being out in front just as easily as writing it out in front. And so then I'll point out that the integral of what's left, the integral of e to the 2x, is easier. It's something we actually just did already. We know that the integral of e to the 2x is 1/2 e to the 2x. So we can totally finish this off and say we're going to get x times 1/2 e to the 2x minus 1/2 times the integral of e to the 2x is 1/2 e to the 2x. And yeah, we could simplify this, or we could not. I mean, sure. 1/2 x e to the 2x minus 1/4 e to the 2x plus c. That's how you can simplify that if you really wanted to. All right. More examples all day. Say we have the integral of, sure, 1 over x times the natural log of x to the 4th power. It's clearly a mixture. I have x to a power, specifically x to the -1, and a natural log of x, also to a power, but we don't really care. So definitely a mixture. We have a log and an any power. Okay. But again, before I start going down the integration by paths, the integration by parts pathway, I should do what? I should try U sub. Is there a good candidate for U? I think so. I think U equal to the natural log of x is a super duper candidate for U, especially because it's actually going to work. If I let U equal that, you guys like, I know it's going to be right because you wrote it over here, not over there. If you let U equal natural log of x, our du is going to be the derivative, which is 1 over x multiplied by dx. And oh, look, I have a 1 over x times dx. So I can totally, you don't have to do this, but I really like rewriting the integral so that the du part is all kind of nice together. I would rewrite this as 1 over natural log of x to the 4th times 1 over x dx. I'm going to be like, oh yeah, my 1 over x dx is equal to my du. How nice. And my natural log of x, that part is my u. So I'm going to rewrite this integral as 1 over u to the 4th du. Now be careful here. I know it might be tempting to say that the antiderivative here is the natural log of u to the 4th. We know that's not right. We know that we should rewrite this as the integral of u to the -4th, and then use the anti-power rule to anti-differentiate it. So we're going to get u to the -4 plus 1 over -4 plus 1, which I would normally skip that step and just say it was u to the -3 over -3 plus c. I don't love negative powers for whatever reason in my final answer, so I would choose to rewrite this as a negative out in front. 1 over 3 times 1 over u cubed plus c. And then finally, plugging back in the fact that u is equal to the natural log of x, I would rewrite this as negative 1 over 3 times natural log of x cubed plus c. Yeah, I multiply those two fractions together to make it one fraction. It's totally fine. Okay. So then, yeah. Let's look at something again. So the point of these problems is really to see that although these integrals might look very similar to each other, sometimes it's going to be a u sub, sometimes it's going to be an integration by parts, even though they have kind of all the same pieces floating around. So let's look at something like the integral of x to the 5th times the natural log of x dx. And now we're not going to write it down, but I'm just going to point out the u sub isn't going to work. So I try letting u equal the natural log of x. The derivative is 1 over x dx, and I don't have a 1 over x. Or if I try letting u equal x to the 5th, my du would be 5x to the fourth, and that natural log of x is still going to be stuck there. So a u sub is definitely not going to play out here. Instead, we're going to try integration by parts. I'm going to try writing the words. No u sub here. Not going to work. So I'm going to do integration by parts. What should be my choice for u? The x to the fifth or the natural log of x? According to our acronym that I was talking about before. Well, I've got a logarithm, so u should equal the logarithm. Here's another way to think about it. When you take the derivative of the natural log of x, what do you get? You get 1 over x, which is a simpler function. On the other hand, if we were to make the terrible choice of letting dv equal the natural log of x, we don't even know what the antiderivative of the natural log of x is. Right? We literally, in fact, that's what we're going to do next. After we do all this, we're going to find it using integration by parts. So, but we're not there yet. We're going to let u equal the natural log of x. dv has to be everything left over. So x to the fifth times dx. Our du, our derivative of the natural log of x, is 1 over x, and we multiply by dx. And our v, the antiderivative of x to the fifth, is x to the sixth over 6. And now we jam it all into the ultraviolet super voodoo. So our integral of x to the fifth natural log of x dx is equal to ultraviolet. I don't actually write u times v. You can if you want. Like, it's totally fine if you want to write out that it's going to be u times v minus the integral of v du, and then rewrite that as u times v with the values plugged in. So natural log of x times x to the sixth over 6 minus the integral of v x to the sixth over 6 times du, which is 1 over x dx. It's perfectly fine to write this every time if you want to. So now, important kind of thing. This first part here is just, it is what it is. It's the natural log of x times x to the 6 over 6, which you could, I don't know, I guess I would probably rewrite this as x to the 6 over 6 times the natural log of x. I don't know why that feels better to me. It just does. And then here we have to be careful. I've seen too many people say that the antiderivative of this incorrectly is x to the 7th over 42 times the natural log of absolute value of x. We cannot anti-differentiate a product by anti-differentiating the pieces and then multiplying together. That's otherwise we would just do this that way. Except we don't know what the antiderivative of natural log is, but you get the point. What we have to do here is simplify this before we try to anti-differentiate it. I'm going to bring out the 1/6 constant, and then x to the 6th divided by x is x to the 5th. And now we're in a great spot to finish anti-differentiating this. So we're going to get x to the 6th over 6 times natural log of x. Notice it's not the natural log of the absolute value of x, it's just natural log of x minus 1/6 times the antiderivative of x to the 5th, which is again x to the 6th over 6 plus c. We got time. We got loads of time. We got a whole 25 minutes still. Right on. So, yeah. Let's do one more. Well, let's do the next one. One more makes it sound like the last one, but you know, it's not. So let's say we want to do, the integral of, let's do that. X squared times sine of 2x cubed dx. Once again, we have a mixture. And once again, it's going to be a u sub instead of integration by parts, because if we let you, right, we can see that the inside of the sine function has a choice whose derivative would be something like this. So I'm going to let u equal 2x cubed. My du is 6x squared dx. I'm going to do it the way I don't like to do it, just for the people that like doing it this other way. I'm going to isolate dx say that dx is equal to du over 6x squared, even though it's not my favorite way of doing it. But some people really like doing it this way. It's totally fine to do it this way. So I'm then going to rewrite my integral as x squared times sine of 2x cubed times du over 6x squared. The x squareds get to divide to 1. And then I can rewrite this as 1/6 integral of sine of replace 2x cubed with u. I feel like that's terrible, but if you like doing it that way, it's okay. And then we integrate sine. The integral of sine of u is negative cosine of u plus c. And then finally, write it as negative 1/6 cosine of 2x cubed. Versus a mixture where we're going to use integration by parts. So let's say we had instead the integral of x squared times sine of 2x. And now a u sub is not the right choice. So you might look at this and accidentally convince yourself that we could let u equal x squared and du would be 2x dx. But we don't have 2x times dx, right? That sine of 2x, that 2x is stuck inside the sine function. It's not actually being multiplied by the dx there. So no u sub, not going to work out. Instead, we're going to do integration by parts. So let's make some choices here. All right, I want all of you to write down your u choice and your d, write down the whole thing. U equals, dv equals, whatever du ends up being, whatever v ends up being. I'll remind you that you're going to pick u according to this acronym. A log if you've got it, a power of x if you don't have a log, a trig function if you don't have either of those things. So I'm just going to ask you all to make sure you're all on the same page. What are we all picking for u in this problem? X squared. Great. Go ahead and do it. Write down the whole thing. Found all the things. You go ahead and start trying to find the interval. Or at least, I'll say you can write down the formula for the interval. I guess I'll give you another few seconds here. All right. So if a big u equal to x squared, then our dv must be the rest. Sine of 2x times dx. Our du is going to be 2x. And our v is going to be the antiderivative sine of 2x, which is going to be negative cosine of 2x divided by 2. Or negative 1/2 cosine of 2x if you prefer. Writing everything out, our uv minus the integral of v du is going to be x squared times negative 1/2 cosine of 2x. I would try to be a little bit forward looking here. Instead of writing x squared times negative 1/2 cosine of 2x, let's write negative 1/2 times x squared times cosine of 2x. It's putting that negative constant out in front, so it's easier to write the things. I'll try to distinguish between my minus signs and my time signs there. And then minus the integral of v du. So that's going to be negative cosine of 2x divided by 2 times 2x. Oh, I forgot the dx there, sorry. Now here's the deal. This integral here, although simpler, right, it's x to the first times the trig function instead of x squared times the trig function, is not simple enough that we know how to integrate it. We have to use integration by parts again. So here's what I would say. I'm going to do one thing before I do that. I'm going to rewrite this. I'm going to simplify this just a little bit. This is negative 1/2 x squared cosine of 2x. Minus a minus becomes a plus, and the 2's cancel to give me plus the integral of x times cosine of 2x dx. And now for this integral here, we're going to do integration by parts again. So for this new integral, we're going to let u equal x. dv is going to be cosine of 2x dx. du is going to be 1 times dx. And v is going to be the antiderivative of cosine of 2x, which is 1/2 sine of 2x. And then we're going to repeat the process. So then this whole thing is equal to this first piece, right? Still there, it doesn't go away. So the negative 1/2 x squared cosine of 2x plus now the entire uv minus the integral of v du. That's going to be u times v, x times 1/2 sine of 2x minus the integral of v du, which is the integral of 1/2 sine of 2x times dx. Couple things here. The reason I wrote brackets around this like this is because oftentimes there'll be some coefficient out here that you'll have to distribute to everything that's in these brackets. So like if this had been like a -3 times this integral, then you have a -3 times this and times this new integral here. All right, we can actually integrate this last piece here. So we're going to be getting the whole shebang, negative 1/2 x squared cosine of 2x plus, I would write this as 1/2 x times sine of 2x minus, let's be careful before I write the minus sign here. What's the antiderivative of sine? Negative. So I don't really want to write minus cosine. So let's write plus, and then it's going to be 1/2 cosine of 2x divided by another 2. And I can double check real quick here. If I take the derivative of cosine of 2x, it will be negative sine of 2x times 2, and that'll give me the negative 1/2 sine of 2x that I was integrating there. So that works out. It's kind of a bit much. And actually, there are a number of problems where you have to do repeated integration by parts, which is kind of annoying. But there is a way of getting around it. And I feel like there was, oh no, I was going to do that first. Yeah. So we'll come back to that in a minute here. How much time have I got? I got 15 minutes. Cool. All right. So let's talk about one example that I think is worth. So I should summarize before I keep going here. So just to kind of see all the things we've talked about, integration by parts you use when you have a mixture, if you've already deduced that U substitution is not a viable option. I will say, technically, there are some integrals that are not mixtures that can also be done via integration by parts, but you shouldn't. For example, and I didn't even know this was a possibility until I saw a student. I was like, oh, you can do that. It's weird though. This integral, the integral of the x times the square root of x minus 1. You should do this with a u sub and a back sub. U equals x minus 1, du equals dx, and then x equals 1 plus u, or x equals u plus 1. And rewrite this as the integral of x, which is u plus 1, times the square root of u, times du. And then distribute, and write this as the integral of u to the 3/2 plus u to the 1/2, and then do the integral. You get 2/5 u to the 5/2. plus 2/3 u to the 3/2 plus c, and then plug back in what your x is to end up getting 2/5 times x minus 1 to the 5/2 plus 2/3 times x minus 1 to the 3/2 plus c. And that should be the end of the story. I will mention, technically, you could do integration by parts here, and it's kind of weird. I think it's weird, actually. I almost don't want to show you because I feel like I don't want to show you, but I don't want to withhold knowledge either. So you could use integration by parts if you really, sometimes your teacher tells you to do it this way. I've seen one web work problem one time where someone was like, do this problem using integration by parts. It's like, oh, that seems strange. But here's how we would do it, I think. We would let u equal x. And then dv is going to be the rest, which is going to be, I'm going to write this as x minus 1 to the 1/2 dx. Let's find the things. And also, you don't need to write this down if you don't want to, because I don't think it's particularly important, but I just want to show you so you can see it. Du is dx, v is the antiderivative of x minus 1 to the 1/2. Well, again, this is kind of one of those mini u substitution integrations that we can just do without doing the u sub. It's going to be x minus 1 to the 3/2 divided by 3/2, or times 2/3. And now, throwing all of this into our pattern, the integral of x times the square root of x minus 1 is going to be u times v. So x times 2/3 times x minus 1 to the 3/2. Didn't mean to get the extra parentheses there, but I do. Minus the integral of v du, which is 2/3 x minus 1 to the 3/2 dx. Simplifying this, you're going to get 2/3 x times x minus 1 to the 3/2 minus 2/3 times the integral of x minus 1 to the 3/2 using the reverse power rule is going to be x minus 1 to the 5/2 times 2/5. And you might say to yourself, James, this answer looks really different. And it does. You could do a bunch of algebra to show that it is the same, but I don't think we should. This answer is the same enough. It might differ by a constant, which is okay for integrals. They're allowed to differ by constants, but actually doing the algebra to show that this expression here and this expression here are the same or similar enough is a non-zero amount of work. So don't do it this way. Not the best way to do it. But technically an option if you really, really want to make it an option. Okay, let's look at another integral that I was alluding to earlier. The integral of the natural log of x. And this might be the only integral of this nature that we encounter in this class. When I say that, what I'm referring to is that this is an integral that requires integration by parts, but you kind of have weird choices to make here. Your choice for u is going to be the natural log of x. And your choice for dv is technically a power of x. It's x to the 0. It's whatever's left. Your dv is going to be just dx, or 1 times dx, or x to the 0 times dx if you like. And then we fill in the things. Your du is the derivative of the natural log of x, which is 1 over x, and we multiply that by dx. And your v, which is the antiderivative of 1, is just going to be x. And then we use the usual thing. The integral of our natural log of x dx is going to be our ultraviolet x times natural log of x. By the way, the reason I write it like this, instead of writing it as literally as u times v, is because if you write the natural log of x times x and you aren't careful, you might accidentally simplify that incorrectly as the natural log of x squared. Like you might think you have x times x there, but we don't. So writing the x in front like that is safer. It makes it really more obvious that you don't have x times x. Minus the integral of my v times du, which is x times 1 over x dx. And x times 1 over x is just 1. And the antiderivative of 1 is just x. antiderivative of the natural log of x is kind of funky, but it is x times the natural log of x minus x. Cool. All right. Yeah, we got time for sure. So let me show you something terrible. I know, it's a really good lead up there. The integral of x to the third e to the x. We're gonna do this one a faster way first. So there are 3 types of integrals where this method I'm about to talk about is applicable. It's really not a different method. It's still using integration by parts, but it's just a shorthand way of doing it. It's kind of like, did any of you ever learn synthetic division? I mean, if you didn't, that's fine. It's kind of terrible. It's a faster way of doing polynomial division, that where you write like weird numbers and like it's all the coefficients and you just kind of do this weird process that doesn't really feel like you're doing anything that makes sense, but you're really just, it's a shortcut way of doing polynomial log division. In a similar way, this process we're going to talk about is not as terrible, first of all. I mean, I'm biased against synthetic division. I think it's not great, but whatever. But this process is not too hard to understand once you see it. So here's what we're going to do. We're going to make a choice for u. If I was doing integration by parts, what would my choice for u be here? Would it be x cubed or would it be e to the x? Oh, shit, I need to plug I forgot to plug my computer. Quickly now, quickly. Don't lose people online. Okay, safe. All right. So what would our choice be here for you? Everybody. X what? Except it's x to the, yeah. And our dv would be the rest. Instead of doing that, we're still going to make the same choices, but we're going to make a table. So we're going to make our u column and our dv column. And in the u column, we're going to start with our choice for u. And then we're going to find every derivative of that until you get to 0. Notably, this only works if our choice of u is x to a positive integer power. Because if it's x to a positive integer power, then eventually the derivative will be 0. Any other type of function doesn't eventually have a derivative that's 0. You keep getting other weird functions. On the right-hand side, in the dv column, we're not going to write the dx part because it's just annoying. And we're going to take all the antiderivatives. So what's the antiderivative of e to the x? E to the x. How about the antiderivative of e to the x? Oh, it's still e to the x? Is it still? Yep, it's e to the x every time. But there are other functions that you can do this with that are slightly more complicated. Also, my function could have been e to the 2x. And then the antiderivative would have been 1/2 e to the 2x. And the next one would have been 1/4 e to the 2x. And then 1/8 e to the 2x, and so on. You take the derivatives of u until you get to 0. You take the antiderivatives of your dv until you have the same number of entries. And then you do the following. You go from your u over and down to the next v, right? Check this out for a second. Look at this for 1 second. If that's my u and that's my first dv, then that's technically my v, and you're getting u times v in your integration by parts formula. But then instead of writing all the work, we're going to do this over and over. You go from upper left to lower right until you can't anymore. And then it's always going to be plus that times that, minus that times that, plus that times that, minus that times that. Always starting with a plus and then alternating every term. So our integral here, our integral of x cubed e to the x dx is equal to plus x cubed times e to the x minus 3x squared times e to the x plus 6x times e to the x minus 6 times e to the x plus c. And this method is often referred to as tabular integration or tabular integration by parts because you're using a table to do the integration by parts faster. This is called tabular integration by parts. It is only for integration by parts. And it is only specifically for 3 types of integrals. Let me tell you what they are. You would think if there's only 3 types, why are we talking about? Well, because they come up often enough that it's terrible. In fact, we have time? Yeah, no, we don't. So here are the 3 types of integrals where tabular integration by parts applies. I'm going to try to write these as generally as possible. So I think of them this way, but I'm writing them kind of the basic case and then the more complicated. So you can either have x to a power times sine of x dx. You can have x to a power times cosine of x dx, or you can have x to a power times dx dx. Couple requirements. Well, actually, one requirement. N must be a positive integer. So it can't be like the square root of x or x to the negative third. It has to be x to the positive 4, 5, 6, 7, whatever nice integer number you like. The kind of thread of commonality here between these 3 integrals is, aside from them having x to the n, sine, cosine, and e to the x are the only functions we really know of, or that we really encounter, where if you do their antiderivatives or their derivatives, they just cycle. Right? The antiderivative of e to the x is just e to the x, e to the x, e to the x, e to the x. For sine, the antiderivatives are negative cosine, negative sine, positive cosine, back to sine. And they just keep cycling over and over. They don't get more complicated no matter how many iterations of them you do. Now, these can be a little more complicated in that instead of having just one of these things, you could have it as really, or not, versus is not, or is the better word there. X to the n times sine of a constant multiple of x. Or x to the n times cosine of a constant multiple of x. Or x to the n times e to a constant multiple of x. And so if it's this kind of version, then when you do this right-hand side here, where you find all these antiderivatives, you're going to end up dividing by that constant at every step. So we don't. What time is it really? Okay. Sure. Let me show you one more thing real quick. So, for example, if I wanted to find the antiderivative of x squared cosine of 5x, sure, we could do integration by parts twice, like we did before with the x squared times sine. Or we could say, well, I'm going to let u equal x squared dv be cosine of 5x times dx, not writing. On the u side, we differentiate till we get to 0. So 2x, 2, 0. We do need the 0 there to make sure we have the right number of rows. On the other dv side, we anti-differentiate. Antiderivative of cosine of 5x is sine of 5x divided by 5. Antiderivative of sine of 5x is negative cosine of 5x divided by 5 twice. And the antiderivative of negative cosine of 5x is negative sine of 5x divided by 5 3 times. Yeah, you can start writing like 5 to the third or 5 squared, but 5 times 5 is 125. And then finally, it's going to be plus this minus this plus this. So my answer here is going to be x squared times sine of 5x over 5 minus a minus is plus 2x times cosine of 5x 25, and then plus with a minus, so minus 2 times sine of 5x over 125 plus c. Certainly a lot faster than actually doing the 3 iterations of integration by parts that would be required to do this problem. Next time, we'll actually maybe do one of the, oh, sorry, not 3, 2 iterations, apologies, 2. This power here, tells you how many iterations you're gonna have to do if it's one of these three specific types. Next time we might do one the long way, just so you kind of see, oh, how it really does work out. But if you have something terrible like this, I think tab usually talks about iteration, or the tabular method. So I think tabular. I think you will see this in class, but even if you don't, it's still a valid method to use, and I would encourage you to use it. Again, only in these three situations. It's only valid there. Other things it doesn't work for. All right, that's all I got. Have a lovely rest of your day.